So our example with Hooke's law deals with the change in the diameter of a steel bolt over here. And so it is measured, the change in the diameter as the bolt is tightened. You've got some material properties. It says determine the internal force. So I want to know what's going on inside the bolt if the diameter is observed to decrease by a very small amount. So again, we're going to be dealing with very small strains, but due to Young's modulus, it'll be significant stresses. So to help ourselves with an axis system, we'll go ahead and put X along the length of the bolt, Y and Z will be perpendicular. And so we can, by what's given to us, we can calculate the strain in the Y direction. So we know that the change in diameter, right, if it decreases, it would be a negative number. Right? The basic definition of strain is equal to the change in length divided by the original length. So we can go ahead and calculate the strain in the YY direction, the normal strain, as the change in diameter divided by the original diameter. So if we go and multiply that out, we just need to keep track of our units. All right, we are inches over inches, so those match up. So we end up with a very small number, something 10 to the minus 6, and that would be called a micron. So we're ready to explore our Hooke's law. So the 3D Hooke's law, right, involves the strain in the Y direction from all three stresses, X, Y, and Z. So this just comes right off of your equation sheet. So normal strain in the Y direction results from a direct stress in the Y direction. It also relates or is produced by a stress X and Z through Poisson's ratio. So let's look a little bit closer at the state of stress all the way back up here. We've got a load that's being applied by the bolt ends as it's tightened. So we've got a stress in the X direction, which would be equal to the internal axial force P divided by the cross-sectional area. Notice on the Y and Z directions, we've got a free surface. So sigma YY and sigma ZZ both equal 0. So we'll take those answers and apply them right here. We just found out that sigma YY was 0. Sigma ZZ is 0. So let's just kind of work through the math here. Those are gone. I'm going to now switch it around, solve for sigma XX is going to be the negative. Right, make sure you keep your negative sign with you. Negative epsilon YY times E divided by Poisson's ratio. So we're pretty close to home here. We've got an expression above for sigma XX, which is just P over A. So we just continue to expose, and if I want to solve for P, the internal axial force, just got to bring A to the other side. So at this point, all we need to do is plug in our values. And as we look to plug in our values, we want to keep our units. We call it the UPD, the Units Police Department. So you want to keep your units consistent. So let's go ahead and look at what our units become. We've got units of strain, which are unitless. We've got E, which is 29 times 10 to the 6 KSI. Cross-sectional area, use 2.5 divided by 2. That's going to be in inches. So those inches squared will cancel with those inches. And in the end, we'll end up with kips. So if we multiply all those numbers together, notice that we've got a negative, two negatives. We've got negative times the strain, and the strain was a negative value. So we end up in the end with a positive number, 94.95 kips, which would be in tension.